Number 33. So we have it passing through 2 points here. We've got passing through 1, 5 and 4, 11. So once again we can use our 2-point equation for a line. Y minus y1 equals y2 minus y1 over x2 minus x1 times the quantity x minus x1. I introduced this in problem 31. So this is actually the formula for slope m. M usually goes here in the point slope equation for a line. So instead of just writing m there, I just put the whole formula there. So we can just plug everything in all in one formula. Alright, so we've got, call that x1, y1. So y minus 5 equals y2 minus y1, 11 minus 5, over x2, that's 4, minus x1 is 1, 4 minus 1, times x minus 1. Alright, so that's 6 over 3, which equals 2. I'll just write 6 over 3, x minus 1, and then make that a 2. Distribute, so you got 2x minus 2, and then add 5 to both sides, so you got y equals 2x minus 2 plus 5, and that's 2x, and then 5 minus 2 is 3, so 2x plus 3. Y equals 2x plus 3, or you can call that f of x if you wish. Okay, number 35. So it's passing through 2 points here. A line is passing through negative 2, 8. And 4, 6. Okay, so once again we can use a 2-point equation for a line. Y minus y1 equals y2 minus y1 over x2 minus x1 times the quantity x minus x1. Alright, so that's, again, call these, this point here x1, y1, and that x2, y2. Alright, so again, you could call that x1, y1 if you wish. You'll still get the same results at the end. But that's y minus 8 equals 6 minus 8 over 4 minus a negative 2 times x minus a negative 2. So 6 minus 8 is negative 2. 4 minus a negative 2 is 4 plus 2, which is 6. And then x minus a negative 2 is the same as x plus 2. Alright, so this reduces to negative 1/3. And then distribute that through, so you'll get negative 1/3 x minus 2/3. Now add 8 to both sides, or transpose the negative 8 to the other side. That'll give you positive 8 on that side, the right side. So that's negative 1/3 x minus 2/3 plus 8. Now what you do is get a common denominator for the 8 there with the negative 2/3. So I've got this, and then minus 2/3 plus 8. Multiply by 1, but choose your 1 to be 3/3. Multiply by 1 so you don't change the value, but now you're going to change the 8 to a 24/3. Alright, still equals 8. So now you have a common denominator. Now so we got negative 1/3 x minus 2/3 plus 24/3. And so finally negative y equals negative 1/3 x. 24 minus 2 is 22/3. So plus 22 over 3. And there you go. Okay, number 37. We have an x-intercept at negative 5, 0 and a y-intercept at 0, 4. So that gives us our 2 points, negative 5, 0 and 0, 4. Alright, here we go with our 2-point equation for a line. Y minus y1 equals y2 minus y1 over x2 minus x1 times the quantity x minus x1. Slightly modified point slope equation for the line where slope m is written out in its formulaic form here. And we can call that x1 y1 and then x2 y2. Alright, so you got y minus 0, which is nice and easy, equals y2, that's 4, minus 0 over 0 minus negative 5 times x minus a negative 5. So it's just plain y on the left side equals 4, and a minus is plus, so that's positive there. Positive 5 in the denominator, so it's just 4/5, positive 4/5, times the quantity, and this is minus is plus, x plus 5, and then distribute the 4/5 through there. You got 4/5 x plus, now you got 4/5 times 5. Think of that as 5 over 1, if you wish. And you can cancel the 5s. Alright, so what you get is 4/5 x plus just 4. 4 over 1 is 4. Alright? Number 39. For the following exercises, find the slope of the lines graphed. So they give us the graphs, and here's a picture of this problem, number 39. You'll note that I've blackened in 2 points on the line. Alright, so you should do that. You don't have to use my 2 points. You can use 2 other points on the line if you wish. And so I chose the x and y intercepts because they have zeros in them, so that makes it a lot easier to compute. Alright, so that's probably the smart way to do it. I hope that's a smart way. Alright, I think it is, because that involves less computation for you. So if you're in a test situation, you know, and you can do it, pick the x and y intercepts if they're nice and integer friendly, as I would say. In other words, if the coordinates are integers. Alright, and it's easy to read that way. So yeah, you can't always do that, but we've got 0, 5 is one intercept. That's your y-intercept. Then you've got 4, 0, which is the x-intercept. Alright, so we need the slope, m, which is y2 minus y1 over x2 minus x1. Rise over run. Alright? And call that x1 y1 and x2 y2. So you got y2, which is 0, minus y1, which is 5, over x2, which is 4, minus x1, which is 0. So 0 minus 5 is just negative 5. 4 minus 0 is just positive 4, so it's just negative 5/4. Alright? There you go. Number 41. For the following exercises, write an equation for the lines graphed. So they give us a line here. Right there. And I've marked 2 points. Unfortunately, the x-intercept is not exactly integer friendly, but it's friendly enough. That looks like negative 3/2 there, negative 1.5, or negative 3/2 as the x-intercept. So that's good enough. Alright, so you can use 2 other points too that are more integer friendly. For example, you got negative 3, negative 1, it appears to be another point on there. So yeah, if you don't want to use what I'm using, feel free, use your own points. But I'm going to use these. We've got negative 3/2 and 0. And 0, 1. Like those zeros, if I can possibly have them. Alright. So we can use a 2-point equation for a line to get the equation for this line. Y minus y1 equals y2 minus y1 over x2 minus x1 times the quantity x minus x1. Alright. So again, we'll call this x1, y1, and x2, y2. So you got y minus 0 equals 1 minus 0 over 0 minus a negative 3/2 times x minus a negative 3/2. So it's just plain y on the left side equals 1 over positive 3/2 times x plus 3/2. Alright. 1 over 3/2, you just invert the bottom fraction and multiply by the top, so that'll be 1 times 2/3, which is 2/3. And then x plus 3/2. Oh, you'll notice 2/3 and 3/2 are reciprocals. So when I multiply that through, that's going to equal a 1. So that's pretty nice. 2/3 times x is 2/3 x plus, and then that's a 1. So there you go. Y equals 2/3 x plus 1. Okay, number 43. So here's a graph of a line provided for us. And I've put dots on 2 points that are on this line that I want to use to get the equation for this line. And so you can pick your own if you wish. The intercepts, well, the x-intercept, I could probably use 1.5 for that, but I'm going to use some integers this time. Alright. So I'm going to use 0, 3, the y-intercept, and 1, 1. Okay, so once again, the 2-point equation for a line y minus y1 equals y2 minus y1 over x2 minus x1 times the quantity x minus x1. So we'll call this x1 y1 and x2 y2. So you got y minus 3 equals 1 minus 3 over 1 minus 0 times x minus 0. So this is negative 2 on top over positive 1, and then just x. So move the negative 3 to the other side, so you're going to get y equals negative 2x plus 3. Well, that was nice and easy. Okay, number 45, and so here's the line. You'll note that it's a horizontal line. What's the y-coordinate for any point on that line? Well, if you pick a point on that line, you'll notice that all the time you're going to get a y-coordinate of 3. So the formula for this line is y equals 3. You're going to have every single possible value for x, every real number for the x-coordinate will be represented as one of the points on this line, and the other coordinate's always going to be 3. So it's some x-coordinate and 3. Okay? So no matter what the x-coordinate is, y always equals 3. So that's the equation of this line. As you can see, I've written in my little notes here, y equals 3. Okay. Here's my note if you want to read that. Okay, there you go. Number 47. For the following exercises, which of the tables could represent a linear function? For each that could be linear, find a linear equation that models the data. So here's our table in 47. Okay, so what we're looking for is rise over run, or the change in y over the change in x, delta y over delta x, is a constant. In other words, when you have a straight line, something linear, the slope is going to be the same, okay, all the way through the line. So if you look at this data, you'll notice that the change in y over the change in x is the same. In other words, take a look. Note that the change in x here is 5 units each time, right? Okay, so that's going to be in the denominator. What's the change in y? Well, it's the same, isn't it? You add the same amount each time and you'll get the results that you see here. Alright, so you've got the same rise over run, in other words. Alright, so what is delta y over delta x? Well, you add negative 15 each time on these y coordinates for the same change in x, which will be 5 in this table, and you get negative 3. Alright, so the slope of this line, it is a line modeling these data points, and its slope is negative 3. Now all we need is one point, and we can use the point slope equation to get the equation of this line. Alright, so you'll note that one of the points on here, The first one is 0, 5. Okay, so we can use that. Why? Because it's got a 0. We'll use the point 0.05. That'll make our computations as easy as we can make them. Slope is -3, so that's m. So you got point slope equation y minus y1 equals m times the quantity x minus x1. There's your point slope equation for a line. So y1 is 5, so that's y minus 5, and slope m is -3, and then x minus x1 is 0. So that's just -3x on the right side. Now you're going to add 5 to both sides. You get y equals -3x plus 5. Alright. Or you can call that f of x if you wish. Or no, call that g of x. Call that g of x because that's what they have on the table, g of x. Alright. So this is called g of x. Now let me elaborate a little bit on what I said before about determining whether or not you have a linear function. Alright. So let's do it over here in the corner. Let's say you have a nonlinear function like that. Okay. Now let's call that distance there delta x, the change in x. So I'm going to measure that same distance on two different parts of the graph. So here's delta x again. Alright. Now what's delta y, or the change in y, for those two intervals? Well, it's the same interval, delta x. Try to make this as neat as I can, but it'll be neat enough to see the result. Alright. Now we'll call this interval delta y1 and this interval delta y2. Alright. So if it's not linear, for the same delta x, for the same change in x, you have different delta y's, or changes in y. Okay, here delta y1 is less than delta y2. If it were a linear function, if you have the same run, you're going to have the same rise as well. Alright? So no matter where you measure the run on the line, delta y, or the change in y, the rise, is going to be the same on a straight line. But on this, it's not a straight line. So as you can see, the changes in y are different depending on where you go on this curve. Alright? Again, you keep the change in x, or the run, the same wherever you measure this. Alright? Because if I were to decrease, the change in x here, that's going to decrease the change in y, and you won't have anything meaningful, alright, to be able to compare. So you keep the change in x the same and measure the changes in y, and you'll notice that in a nonlinear function the changes in y will be different depending on where you go on the graph. Alright? So that indicates you don't have a straight line. Okay, so you'll see a lot of this kind of stuff going on in calculus, a lot of these kinds of graphs and notation. The deltas, meaning change in, that's uppercase Greek delta. You'll see lowercase Greek deltas, which means something else too. Alright, so it's good to get used to it here, maybe even if you're not taking calculus, you might want to take it later or just study it and on your own. Alright, so it's good to be exposed a little bit to it here. Well, that's what pre-calculus is all about, exposing you to calculus, or beginnings of the ideas of calculus, getting you used to all these little formulas and Greek letters and so forth. Alright, so it's not terrifying. It's actually a very powerful language and tool to describe all kinds of phenomena. So if we didn't have the symbolism, we'd have to use plain English, and in some cases that would make it practically impossible to read or teach, alright? So, or to work with. So the symbolism is absolutely necessary, and it's a beautiful creation of the human mind. So don't shy away from it. Learn it, because it's a beautiful gift to you from the human race. Okay? Alright. There you go. Okay, number 49. So here we have a table. Alright. Note that the changes in X are the same, 5 units for each change. Question is, are the Y's changing in a constant way? Well, yeah. The change in Y over a fixed change in X is constant, so this is a linear function. Alright. So I'm going to use 2 points here. We have, if you look again at the table, we have 0, -5, and 5, 20. We could use those 2 points, or you could use any other 2 points in the table. Alright. But I like the zeros in there, and I like the small integers, alright? So why make it hard on yourself? But then again, I'm not a student anymore, so I can see some value in maybe making it hard on yourself just to challenge yourself and expand your mind a little bit. But as for me, been there, done that, so I'm going to go the easy way now. Alright. So I've got 2 points, and I need an equation for the line, and I'm going to use the 2-point equation for the line. Y minus y1 equals y2 minus y1 over x2 minus x1 times the quantity x minus x1. Alright, we'll call this x1 y1 and x2 y2. Alright. Alright, so we've got y minus a y1, or y minus -5 equals y2, which is 20, minus y1, which is -5, over x2, which is 5 minus 0. Times x minus 0. Alright. So y minus a -5 is y plus 5. And that becomes 20 plus 5, which is 25, over 5 minus 0, which is 5. And then we have just x there. Alright, so 25 over 5, of course, is 5. So we've got y plus 5 equals 5x. And then subtract 5 from both sides, y equals 5x minus 5. Alright. So there you go. Or call it f of x, because that's what the table calls it. F of x equals 5x minus 5. Alright, so there you go.